Hi, thanks for coming to the talk. As Ryan just said, I'm Douglas Anderson. I can be found online pretty much everywhere as Hockey Buggy. The title of this talk is Slots, 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 Everybody, an exploration of DunderSlots. This is, of course, a reference to the band LMFAO, but we won't be talking about them today. Instead, we'll be talking about some low-ish level Python. Before we get to that, let me quickly introduce myself. I'm from Toronto, and I participate in some really cliche Canadian activities, such as canoeing and curling. As Ryan said, I work at Wave, and we're a fantastic growth stage startup in Toronto, and we're hiring. Come find me if you have questions about that. Let's quickly cover a definition. This is the thing that I'm going to be talking about, and I'm going to refer to it as DunderSlots. Dunder is just short form for double underscore. What are we going to discuss today? In the next half hour, we are going to talk about a high-level introduction to slots. And we're going to go a bit deeper and talk about how slots works. We're going to talk about some of the good things. After that, we're going to be talking about some of the trade-offs. Then we're going to talk about some alternatives that we could consider. And finally, we'll wrap things up and hopefully have time for questions. So why am I giving this talk? This is the reference material to DunderSlots. This is all of it. It's about 422 words long. 22 of them is the word DunderSlot. Don't get me wrong, it's a really good document, it's very comprehensive, but it's a reference doc, it's not a tutorial, and it's not really necessarily the best introduction to DunderSlots. But if we grep for DunderSlots in Python source code, we'll find that it's really heavily used in the standard library. This makes me ask, why is it so heavily used in the standard library? And should I be using DunderSlots in all of my classes? The goal is that by the end of this talk, all of us will have an answer to these questions. This is from the data model reference doc that we saw earlier. It says, the DunderSlots declaration takes a sequence of instance variables and reserves just enough space in each instance to hold a value for each variable. Space is saved because DunderDict is not created for each instance. This is a really good high-level description. Let's try and illustrate what it's saying. The last line there, space is saved because DunderDict is not created for each instance. In order to understand this, we need to talk about how attribute storage works normally. Let's start with this class, sans-slots. Its constructor takes 2 arguments and stores them as instance attributes. When this class is instantiated, the Python interpreter will make a system call to the operating system in order to allocate some memory. Let's take a conceptual view of what the interpreter does with this memory. Here we have the class sans-slots, and when we instantiate the object, the interpreter creates a new object instance and a new dictionary to store attributes for that instance. Here we see that it has the keys red foo and sky blue. This is the same thing, just rearranged a little. When we create a new instance of the class, the interpreter does the same thing as last time. It allocates memory for the instance and for the dictionary. See that we're storing almost the same dictionary twice, just the values are different. Now, let's talk about DunderSlots. Here is our new class of xslots. Xslots is the same as sans-slots with one exception. Xslots has a DunderSlots definition right there. A DunderSlots definition is a class variable that you assign a sequence or an iterable to. Each value in this sequence represents an instance attribute that space will be allocated for. Here is another conceptual view of what this looks like in memory. It's a little different than the instance of sans-slots. Notice that we don't have a DunderDict. Instead, we have the values in a densely packed array and a lookup thing that in this conceptual view I'm calling a map. This map contains an offset into the array for each attribute. When we add another instance, we can save space by reusing the same map. Notice that we no longer have multiple copies of red foo and sky blue and the associated overhead of having an attribute dictionary per instance. So the interpreter does two things differently when it comes across a DunderSlots declaration. First, it no longer creates a DunderDict. And second, it creates data descriptors for attribute access. This is the thing that I was referring to as a map a little bit earlier. And you may be wondering, what are data descriptors? Field, in this case, is a data descriptor since it implements one or more of the methods DunderSet, DunderGet, or DunderDelete. When we access the X attribute of the model instance, instead of going through normal attribute access, it will use the descriptor. So if we create an instance of the model, set a value on it, and then get that value, we see that some additional printing has happened because attribute access is going through the descriptor rather than normal means. For those of you who have used Django, this may look familiar since fields in Django models are implementers of descriptors. If you're still curious about descriptors, Jesse Shapiro will be talking about them at the 420 slot in this room a little bit later. By using descriptors, DunderSlots is able to store and access instance attributes without having a DunderDict behind it. So now that we are starting to have an idea of how DunderSlots works, let's talk about some of the benefits. The most obvious benefit is that it uses less memory. A potentially surprising benefit is that it actually makes attribute access slightly faster. Let's talk about some experiments I ran to demonstrate this. So how can we find out how much memory DunderSlots is saving us? Well, the standard library has a module for that. The TraceMalloc module allows us to record the memory allocations that the interpreter is making. We will use TraceMalloc to run our experiment. This class implements DunderEnter and DunderExit, so it is a context manager and can be used with the with statement. All that this does is starts tracing on enter, stops tracing on exit, and makes the number of bytes allocated accessible as an attribute. Now, we can use this tracer context manager in this function called measure. It's going to make a list of n instances of class and return how much memory was just allocated. We're going to use that function with our old friends, vexslots and sandslots, and to print the results. So, according to this benchmark, we save around 10 megabytes with, I believe we made, so that comment is slightly wrong. Instead of one instance, we in fact made 100,000. Many, many attributes. I should add commas. So around 10 megabytes. The slotted class takes almost 1/3 the memory that an unslotted class does. This is a pretty significant memory saving. Now, earlier I made the claim about DunderSlots making attribute access slightly faster. Well, in 2010, Guido van Rossum, the benevolent dictator of Python, had a really interesting blog post on some of the details of what in Python 2 was called new style classes, which we call classes today. One of the interesting things he mentions near the end of it is the reasoning behind slots. In the post, he says, some people mistakenly assume that the intended purpose of DunderSlots is to increase code safety by restricting the attribute names. In reality, my ultimate goal was performance. Not only was DunderSlots an interesting application of descriptors, I feared that all of the changes to the class system were going to have a negative impact on performance. Using DunderSlots makes attribute access slightly faster. So how can we measure this? The standard library saves the day again. The Timeit module does exactly what we want. It takes a snippet of code, executes it many times, and returns the total amount of time it took to run that snippet. This is a different measure function that makes the class under test available in the statements above it, creates an instance of that class, and then this statement is going to be run each iteration of Timeit. And the only thing that this statement does is it accesses the attributes of the instance. It doesn't do anything with them. Then we run that statement 1,000,000 times and return the total amount of time that it took. We will run this again for our favorite classes of XSlots and SANSlots and print some results. And the results are a little bit variable. So I ran this a few times. For slotted classes, accessing attributes 1,000,000 times took around 7/100ths of a second. For unslotted classes, accessing attributes 1,000,000 times took 1/10 of a second. So based on this experiment, accessing attributes is around 30% faster. This is a pretty tiny benchmark, so we shouldn't put too much faith in its results, but it does show that attribute access is slightly faster with slots. So up until this point, we've only been talking about the good things that DunderSlots does. Now let's talk about some considerations we should make before we add slots to all of our classes. One of the biggest limitations to slotted classes is that it can only store attributes defined in the DunderSlots iterable. Here we see that if we try and set the attribute patron on an instance, we get an attribute error. This can be both a good thing and a bad thing. Having to add a new attribute to the slots declaration before you can use it can potentially positively inform the design of your code. Remember that before we add DunderSlots to a class, we need to know all of the attributes that we may set on it. Another potential limitation of DunderSlots is that subclasses won't respect the DunderSlots declaration in its superclass. So here, we subclass of XSlots and assert that, like instances of its parent class, sub of XSlots doesn't have a dunderdict attribute. But if we run this, we get an assertion error. This subclass does have a dunderdict. One might think that if a subclass's instances have a dunderdict, then maybe DunderSlots wasn't inherited somehow. But the subclass still has a DunderSlots attribute, and it actually has the exact same value as its superclass. So what's going on here? A DunderSlots declaration must be in the class definition for it to have effect. Well, the DunderSlots can be inherited. The behavior is not. If we want to be slotted, then we have to redeclare the DunderSlots again. As you can see, we don't have an assertion error this time. Personally, this seems like an okay trade-off to have to redeclare DunderSlots in some classes, but it does add some cognitive load to when we're changing our code. So now let's take some time and consider some alternatives. Before we add slots to everything, there's one change that could save us a huge amount of memory, and that is not keeping so much in memory. Keep in mind that DunderSlots is a micro-optimization in some ways. There are other macro things that we should absolutely consider first. Consider, do we need to have all of these objects in memory? Is it possible that we could use an iterator instead? Could I use a database or an external memory store? Sometimes the answer to those questions is no. But before we use slots, we should consider one other alternative. What about named tuples from the collection module? Named tuples will still allow us to access attributes like values like instance attributes, but they're backed by tuples rather than object instances. There are some things that could make named tuples less than ideal. For example, the syntax doesn't look particularly familiar. They're immutable, which might not be appropriate in all use cases. They're quite hard to inherit from because they're not descendants of object. And up until recently, you weren't able to add type annotations to named tuples until in Python 3.5, we got the typing named tuple. It's pretty neat. It has a much more familiar syntax than the collections named tuple, and I really encourage you to check it out. So how do named tuples compare to slotted and unslotted classes? Let's use the measure functions that we used before. And named tuples compare sort of as you might expect in terms of size. They're 20% larger than slotted instances, and they're about half the size of unslotted instances. The speed of attribute access is actually a bit surprising here. There we go. Named tuples take almost twice the amount of time to access attributes. They're actually relatively slow when compared to accessing attributes off of an object. I found this quite surprising personally. So what have we learned today? Well, we hopefully have an idea of how DunderSlots works. We know that there are some good things about it, such as we can see that it improves memory usage. It makes attribute access slightly faster. There are also some less good things. For example, DunderSlots adds another thing to keep track of in your head. You have to remember what attributes are on each class, and you also have to remember to redeclare slots when you're inheriting from it. So inheritance can be sort of tricky. And we've learned about some other things that we could reach for before reaching for DunderSlots, such as keeping things out of memory. Whenever possible, it will always be smaller to not have something in memory rather than keeping smaller things in memory. As well, named tuples can often be used in place of slotted classes. So DunderSlots is definitely a useful language feature that Python has. It can make sections of code with many live objects use less memory. But if you're optimizing code, there are some other things that you should consider first. Hopefully today you learned some things that can make you make slightly more informed decisions and allow you to make your objects both faster and smaller. Before we go to questions, I'd like to take a quick second to thank some people. The numerous people who helped me write and edit this talk. My Uncle David for introducing me to computers. The sponsors for funding this shindig. And thanks to all of the volunteers. Does anyone have any questions? Yes?
Is there any distinction between the typing name tuple and the collections name tuple, or are they essentially the same thing?
I actually haven't looked at how the typing name tuple is implemented. I know that the collections name tuple is an eval statement that is apparently safe, so I don't know if they're the same. Does anyone know? Cool. All right. Yes?
You mentioned with inheritance you had to rewrite the names of the particles.
Right.
Would it be possible, for example, to access your parents' variables and just assign it to your current class?
Yes, you could definitely type super close paren, open paren, close paren, dot DunderSlots, and then append on whatever you wanted afterwards. You don't necessarily have to retype everything as I showed in the example. That is a good point. Yes?
You mentioned when you do it double instances on one class, that it will share the same path.
Right,
If you have an inheritance,
right.
will it share the map with its parent or will it create its own?
It will, you'll have to redeclare it. So it won't share the parent. It will have its own set of descriptors that are what I refer to as a map there. Yes?
Do you guys use weight
Mhm.
slots information and how to measure the differences on the
We actually only have one place that I'm aware of where we're using slots. We're using it on the team that I'm in. And part of that was we got to start a greenfield project. And so because of that, we're on Python 3.6 and we wanted to experiment with it. And so we have slotted classes that have MyPy and type annotations, and it's definitely the nicest project to work on at Wave, in my opinion, my extremely biased opinion. Yes, Jesse.
So with the slots, you're accessing the item in the iterable through a descriptor. So in a dict-backed class, you can have a name on the class dictionary
Right.
and access it with self. And then also set self dot that name and set it in the instance. Is that a pattern that you can do with a slots-backed class?
I'm unfamiliar. So sorry, can you go back to the first example of setting an attribute? You're saying that you can set it inside the class?
Right. So
Yeah.
with my init statement, say I have this variable x,
Mm-hmm.
and I want to have this default variable, this default value for all my instances. In my class definition, I can say x equals 100.
Right.
And then in my init, I can say x equals self.x
Or the value that was passed in. Right. I'm pretty sure that you can, as long as you have that default attribute inside of your slots definition. Cool. If anyone has any more questions, I will be actually just down here. Thank you very much for coming to see my talk.